Hello, hello, hello. Welcome back to 3200. Today we have a cool lecture, I think. Today we're going to be talking about temporal difference learning and the Q-learning algorithm, which is probably the most famous reinforcement learning algorithm. How's everyone doing out there? Hope everything is going well with you. Had a nice weekend, etc. So let's look at where we are in the class today. Tonight, assignment 4 is due, so make sure you get that in. I'm sure there's a bunch of people actively working on that right now, so you'll be catching this on YouTube, I'm sure, rather than watching it live. Yeah, we'll talk about temporal difference learning, and then we'll go over assignment 5. The explanation of assignment 5 should be quicker than some of the previous assignments, because it's actually not that difficult to do. So what I'm going to do is just jump right into it. So let's get into our slides. Here we go. PowerPoint time. Okie dokie. So today, as I said, is it lecture 17 or 18? Can't remember. Either way, we're going to talk about on-policy learning versus off-policy learning. We're going to talk about temporal difference learning, and then we're going to give two different temporal difference learning algorithms, namely Sarsa and Q-learning. And there's some tiny differences between those algorithms, but they end up being very important differences. And by the end of this lecture, you'll be able to implement them no problem. And then I'll explain assignment 5, and assignment 5, you'll actually be implementing the Q-learning algorithm. But first, let's talk about on-policy versus off-policy learning. And this is in the textbook starting at chapter 5.4 to 5.6. So I've just given a link there to the online HTML version of the textbook where you can read more in depth about this. And with the reinforcement learning stuff, because we have a really good textbook, right, I'm giving sort of the abstract version of things in the slides. I'm not going super in depth with anything, but please, for the exam, make sure you read the relevant sections of the textbook. So, recall the Monte Carlo exploring starts algorithm that we presented before. So if you haven't seen that slide, you'll be a bit lost for this one, but just go back and watch the previous lecture for that. So what we did was we used the current policy to update our values, and then we used those values to update the policy, right? This was the sort of general policy iteration that we were talking about. In that case, what we were doing is we were improving the same policy that we were using to make decisions and guide learning. So if we are using the same policy to guide our actions, and then we're actually updating that policy within the same GPI loop, that's called on policy, okay? So if we are improving the same policy that's being used to guide the learning, then that is on policy. Off-policy methods learn a different policy than the one that's used to generate data. So for example, if we were watching someone take random moves in an environment, that would actually be able to tell us something. We can learn stuff from that, right? So if we used random moves to generate rewards and stuff and move around in our environment, then we can use that to learn a policy that may be way better than random. Or for example, if we were observing human actions and then learning something from those human actions, then that would also be off policy. So again, what this is, on policy, we use the actions that guide our policy. We're improving the same policy that is used to make decisions. In off policy, we are learning a different policy than the one that's used to generate the learning data. Okay, so that's the big difference, and something about that will definitely be on the final exam. So Monte Carlo policy iteration, just recall this. We did this last time, okay? So we stored our initial value estimates. We have a policy which is initially equiprobable. And then for some number of iterations, what we do is we generate an episode based on the policy. We update the values based on the returns of that episode, and then we update the policy to choose the actions with the max values. So here what we're doing is we are generating the episode, so we generate the learning episode with the policy that we then update. Okay? So on policy means that we generate episodes based on the policy we use to update. All right. So an off policy example would be the following. It's the exact same algorithm, except, for example, if we generated our episode with random actions instead. Okay? So if we generate our episode with random actions instead of the actions of the policy that we're learning, then this is off policy. So the policy we form does not guide the episode generation, right? So the episode generation is being done with random actions rather than the policy that we're actually learning. So why does all this matter? So again, on policy uses the same policy that's used to generate the actions, and off policy updates a different policy than the one used to generate the actions. So when we're doing on policy learning, it learns a policy that takes things like exploration into account. So for example, if we're using epsilon greedy to guide our actions, then an on policy learning will learn to deal with those random actions of epsilon greedy. And I'll show a good example of this later. Off policy will not take those things into account. So a general trend that you will find is that if you're doing off policy learning, it can have poorer performance while you're doing the training. Okay? But it may result in a better policy or better performance after the learning phase has been completed. So on policy may have better online performance versus off policy, but you're learning a policy that takes the exploration into account. So if you're doing something, for example, where you're generating a bunch of training data and learning with reinforcement learning, then an on policy learned policy after you've finished the training may not be as good as an off policy learned policy. So on policy control methods. In on policy, the policy is generally something that we call soft. So in a soft policy, it means that the chance to choose every action is greater than 0. And mathematically, we represent that by saying the policy pi. So the probability that an action is A given a state S is greater than 0 for all states and all actions. So a soft policy means that every action has at least some probability of being chosen. As it learns, the policy moves toward a deterministic optimal policy, but it's still always going to have some chance of choosing all actions. An example of on-policy methods is to use an epsilon greedy policy to select actions. So we talked about that before, right? So if we have epsilon greedy, then with probability epsilon, we choose a random action. And so therefore, if epsilon is greater than 0, then every action at every state has a possibility of being chosen. And so that means that epsilon greedy results in a soft policy. So epsilon greedy on policy control. So what we do for this is with probability epsilon, we choose a random action. With probability 1 minus epsilon, we choose a greedy action. So what does that mean? Let's say that our epsilon is 0.1, okay? So 0.1 means that 10% of the time we choose a random action. And if 10% of the time we choose a random action, that means 1 minus 0.1, or 90% of the time, we choose the greedy action. So in an epsilon greedy policy, non-greedy actions have probability epsilon over the number of actions in the set, and greedy actions have probability 1 minus epsilon plus epsilon over the number of actions in the set. And I'll do an example of this that shows you how that math works out. And so this is an example of an epsilon-soft policy, okay? So this means the probability of choosing A given a state S is greater than epsilon for all states, actions, and some epsilon greater than 0. So that's just another definition. And we'll show all this in algorithmic form, and to me it makes more sense in algorithmic form. So we'll see that in a few slides. Monte Carlo generalized policy iteration with an epsilon-soft policy. So on policy, Monte Carlo is still generalized policy iteration. So if we look back to the slides we did last time, we use first visit Monte Carlo to perform policy evaluation and estimate the current policy. So that was the first step of generalized policy iteration. Without exploring starts, if we simply make our policy greedy with respect to QSA, we never explore, and so many state action pairs go unvisited. So Epsilon-soft on-policy methods ensure that exploration occurs and all state actions get visited. So what those last two sentences mean, if we revisit the last time, we introduced exploring starts and epsilon greedy in order to ensure that our agent is going to A, start in a random place in the environment, and at least sometimes choose random actions. And the reason that we do that is because we're doing reinforcement learning. We're learning from our mistakes. We're learning from our good actions. And so we want the agent to visit all places in the environment eventually so that we can learn a lot about them. So that's just another way of saying that. But what happens is, now that we're learning using random actions and exploring starts, the policy that we learn is only optimal within all Epsilon-soft policies. But in practice, it's still quite good. So what that means is, with this method, we may not learn the exact optimal policy, but we're getting something close to the optimal policy. Okay. So on-policy methods update the policy with the randomness of epsilon greedy included. If the environment has hazardous features with strong negative rewards, epsilon greedy will encounter them. And so that's going to result in a policy that can be overly cautious and not globally optimal. And so I know this is a little bit difficult to understand, but I'm going to have a really good example from the book in a few slides. And this will definitely explain things in a more intuitive way. And also go over and read this part of the book because it's really excellent and the examples they give are great. Okay, so here's how we look at this algorithmically. So this is on policy, first visit Monte Carlo with an epsilon-soft policy. So the initialization. We initialize our state action values with some initial value, maybe 0. And then we also initialize an equiprobable policy. So we looked at that last time. And then we repeat forever, right? Or until we want to stop learning. We're going to generate an episode using the policy P, right? So we generate an episode. We went over that last time. Then for each state action reward tuple in the episode, we calculate G, which is the return following the first occurrence of the state and action pair in the episode. So that's what we did last time in first visit. And so what we do now is we can apply any update rule to update our value estimate of that state action pair. So here we're using the step size update rule, which says that the new estimate is equal to the old estimate plus the step size times the return minus the old estimate. And if you're not sure what that line means, go back a lecture or two and look at that. Then for each state in the episode, now we're going to do the policy update. So what we're going to do is we're going to find the action which maximizes QSA. And so all we do there is we look over all the actions at a given state and choose the maximum one. And I'll have a numerical example of this to make it more intuitive on the next slide. And then for each action A in A of S, and big A of S, that's the set of all possible actions at a given state. If we have the maximum action, then the probability or our policy at the probability that we should choose that action at that given state is 1 minus epsilon plus epsilon over the number of actions. And the probability that otherwise, if that's not the maximum action, we should set that to epsilon divided by the number of actions. Now, that's a little bit hard to understand, okay? But here's a numerical example which will explain it. At least this is how I ended up understanding it. So let's take the example that we've been going with so far, and what we'll use for assignment 5 is the example of like pathfinding, for example. So if we're at a current state, we have a number of different directions that we can go in. Let's say we can move up, down, left, and right. And so let's just say that up is action 0, down is action 1, left is action 2, and right is action 3, okay, just for example. So we'll use this example to calculate, to do a sample calculation of the algorithm that we did on the last slide. So here's an example Epsilon-soft calculation. Okay, so that is what we just showed. This is the part of the algorithm that we're working with. So let's just say we have the following parameters. Let's say we have an epsilon equal to 0.1. So that means that with 10% probability, we're going to choose a random action. And we're going to have 5 actions that are possible at a given state. Okay, I know I just said 4, but I put 5 on this slide. So let's say that our value estimates, after we do an episode and after we update, these are the values that we have. So we have 10 at index 0, 20, 15, 5, and 10. So let's just say we have 5 possible actions, and at this given state, the values of those actions are these right here. Okay? So what we first have to do is line 2 up here, which says find A star, not the A star search algorithm, but this is the best A. And so we're going to find this value, which is the action that maximizes Q of SA. So if we look through here, which of these values is the highest? So it's this 20. I've bolded it here for you. And so the action which maximizes Q of SA is action 1, right? So this is index 0, index 1, index 2, index 3, index 4. So A star equals 1. So that's what we set right there. Now, if we're trying to do the policy update for the next time step, what we do is the following. We have, if the action is equal to the best action, then we use this formula. If the action is not equal to the best action, then it's equal to this formula. So let's think about this for a second. We're saying that with 10% probability, we want to choose a random action. That means with 90% probability, we want to choose the best action, the greedy action, right? So if we have 5 things, if we have 5 actions, and with 10% probability, we're going to choose a random one, what is the probability that I choose any specific one of those on the random action? Right? Well, it's 1 over 5. Right? Because we have 5 actions. Oh, sorry. 1 over 5 times epsilon. Right? So this is epsilon over 5. So it's 1 over 5 chance of selecting each action times epsilon. So this would actually be epsilon over 5, epsilon over 5, epsilon over 5, epsilon over 5. Okay, sorry that that's a little bit hard to read there. So this is this part right here. It's saying that, let's say that this is the maximum action for now, right? Because this was the maximum action over here. So if it's not the maximum action, what we do is we set the probability of it being chosen to epsilon divided by the number of actions, right? So that's the calculation. The only difference is for the maximum action, we want that to be chosen with 90% probability, right? So whenever we don't hit that epsilon, we're choosing the maximum action. So here for this one, it's 90%, but we also have the probability of choosing it randomly. And so it's 90% plus epsilon over 5. Okay, so that's what this all means. This 1 minus epsilon, that's the 90%, and right here, this is the chance that it'll be chosen randomly. Okay, so if we look at these values then, this one here is the maximum action, which correlates to this index down here. So I just plugged in the numbers. So these, anything but this one, are the non-greedy actions. So we do the else, okay? So this one is 0.1, which is epsilon over 5, which is the number of actions. This one here, we have 1 minus epsilon, which is the 90%, plus 0.1 over 0.5. So that's this formula here. And then here, here, and here, they're also non-greedy actions, and so we apply this formula to those. Okay? So if we actually do the math, then what we have is the chance of choosing the first action is 2%. This one is 92%, 2%, 2%, 2%. And the reason for that, intuitively, is that we wanted this one to be chosen 90% of the time, and then 10% of the time we choose a random action. So if you have 5 actions and we're choosing one randomly 10% of the time, then each action has a 2% chance of being chosen. So of course, we add that 2% to the 90%. Okay, so that's the example Epsilon-soft calculation, and I hope that that's a little bit more intuitive to you now, because you may have to do a calculation like that on the exam. Okay? Perfect. Now we've done that, let's talk about off-policy methods. Here's the learning control methods dilemma. We want to learn actions. We want to learn action values based on what we currently believe to be the optimal behavior. But we need to behave non-optimally in order to explore the state action space and actually find the optimal behavior, right? So we want to learn the things that are good, but we have to explore to find the things. And so you remember what this was called? This was exploration versus exploitation, right? So we're still talking about that. On-policy Epsilon-soft methods compromise by finding a near-optimal policy that still explores. But we don't want that exploration necessarily. Another approach is to use 2 policies, okay? So we're going to have the target policy. The target policy is the policy that's being learned over time. And we're going to have the behavior policy. And the behavior policy is the one that's actually used to generate the episodes and do the exploring. So we're learning from data that is off the target policy. And so if it's off the target policy, it's off-policy learning. Okie doke. So on-policy methods generally are simpler than off-policy methods. Off-policy methods require additional concepts, they have higher variance sometimes, and they may converge slower than on-policy methods. But off-policy methods are more powerful in general. And it turns out that actually an on-policy method is actually a special case of an off-policy method where both the target policy and the behavior policy are the same. Okay? And we're not going to get too detailed into the explanation of off policy and all of the mathematics behind that, but I will give 2 of the more popular algorithms for on policy and off policy learning. And I know this all seems a little bit confusing and there's lots of formulas and numbers and algorithms being thrown at you, but at the end, really what you need to know at the end of this lecture is the Q-learning algorithm, and it's actually so simple and so beautiful, like you'll be able to remember that, no problem. Okay, so now we're going to get into temporal difference learning, and that's in chapter 6 of the reinforcement learning textbook, and I've just included a link here for you. Oh, excuse me. So what is temporal difference learning? It is a central idea of reinforcement learning. It's very, very important. And this is where, I guess, modern reinforcement learning sort of starts. We're going to combine the ideas of Monte Carlo methods and dynamic programming methods. So, like Monte Carlo methods, temporal difference methods learn directly from experience without a model of the environment. But like dynamic programming methods, temporal difference methods update and incorporate other learned estimates without waiting for the final outcome of an episode. And this is called bootstrapping. But this relationship is very important. So the relationship between temporal difference learning, Monte Carlo, and dynamic programming is important. And like dynamic programming, the big difference from Monte Carlo is that instead of just doing the update based on the episode, the TD method update, it incorporates other learned estimates into its update function. So we'll see how it does that, But just like dynamic programming, where it uses the value of its neighbors, temporal difference learning is also going to use those values. So, temporal difference prediction. Both temporal difference and Monte Carlo use experience to predict the value of a policy, okay? So that means they generate episodes, or in a continuing task, they just keep going. Monte Carlo methods wait for an episode to finish, then update the values based on a final return after the episode is done. But temporal difference methods, they don't wait. They're going to update values after each time step. So we're no longer going to generate an entire episode and then come back and update everything. We're going to do updates after every action is taken. And it turns out that this is extremely powerful, and it's actually much easier to implement in practice. Because all you're going to do is have a very simple loop where in your assignment, you do an action, you get the reward, you do the update, that's it. And you don't have to generate a whole episode, wait for it to finish, come back, loop through the episode. It's not like that at all. So, what is the temporal difference prediction target then? So, Monte Carlo uses episode return as the prediction target. Remember? So we said the value of a state is equal to the previous value of a state plus alpha times the return of the episode minus the previous value of that state. But temporal difference learning is going to use the next reward and the next state's value. Okay? So, the value of a state is going to be equal to the value of the state plus alpha times, instead of computing the entire return for the episode, this is going to be done in real time, right, after each action. So we can't compute that entire return because we don't know it. We're not doing an episode. So we're going to use the immediate reward plus the value of the state that we're going to. So here inside the alpha multiplication, we have the next reward plus gamma times the value of the next state. And this is an important distinction. So temporal difference updates immediately upon transitioning to state st plus 1 and receiving rt plus 1. So the temporal difference target for the update is this value. It's the reward that you get plus gamma times the value of the next state. That's called TD0, or one-step TD. Now, in general, this 0 can be replaced by a parameter called lambda, and we have TD lambda. We're not going to get into TD lambda in this course. I have other things after this lecture that I want to teach you, but just be aware that that sort of thing exists. So what TD0 means is that we're going to look at the next reward and the value of the next state. And if we look at this, this is actually very similar to the Bellman equation. So this comes from the Bellman equation and the dynamic programming update formula. So here's tabular TD0 for updating the value of a policy. Initially, we have some policy, and we're going to have the value for each state, and then we repeat forever. You're going to have a starting state for your episode, then repeat for each state of the episode. You have A, which is the action given by your policy for state S. You're going to say, okay, do the action A at state S, and we come up with S prime. Then R is the reward from doing A at S. Then we use the TD0 update formula, and then we set S equal to S prime. And that's it. We just literally implement what we saw on the next slide. It's very, very simple. There's no generating of entire episodes and storing them and then iterating through each one. We just update in real time. So the value estimate uses the next state value in its estimate. So if we remember, now I'm not going to explain all of this right now, but go back to that derivation that we did in the dynamic programming slide. So the value of a given policy at a state, the value of a state within a given policy is the expected value of the return from that time step given that policy. And this is equal to the next reward plus gamma times the return following the next state. And so we derived this formula earlier, so I don't need to do it now. But this is equal to, well, what's the return at time t plus 1? Well, that should be, ideally, the value at state st plus 1. And so what we're doing is Monte Carlo methods use this formula as the target. Dynamic programming and temporal difference methods use 3 as the target. But as we go to infinity, these are actually the same. So as our number of time steps goes higher and higher and higher, the expected value of the return from time t is the same as the expected value of the reward at t plus 1 times gamma times the value at state t plus 1. It's just that in Monte Carlo methods, we generate the whole episode and use the return. In TD, we don't have the return. We're updating after each time step, and so we use the value of the next reward and the next state. And so temporal difference learning combines Monte Carlo sampling with a dynamic programming update. There you go. So that's the difference between them. Now, I am going to read out this example because it's straight from the book and it's excellent, but please go read this part of the book and read their explanation of it as well. It is vital that you explain this difference. And this is an example. It's about driving home. And it shows you the difference in how Monte Carlo methods would update an estimate of the drive home time, and temporal difference methods would update that. So let's just read along. And I hate reading from slides, but they phrase it so well that I'm just going to read it. Okay, so each day as you drive home from work, you try to predict how long it will take to get home. When you leave your office, you note the time, the day of the week, the weather, and anything else that might be relevant. So say on Friday, you're leaving at exactly 6 o'clock, and you estimate that it will take 30 minutes to get home. As you reach your car it's 6:05, and you notice that it's starting to rain. Now, you know that traffic is often slower in the rain, so you re-estimate that it will take 35 minutes from then, or a total of 40 minutes. 15 minutes later, you've completed the highway portion of your journey in good time. As you exit onto a secondary road, you cut your estimate of total travel time to 35 minutes. Unfortunately, at this point, you get stuck behind a slow truck and the road is too narrow to pass. And you end up having to follow the truck until you turn onto the side street where you live at 6:40. 3 minutes later, you're home. And so the sequence of states, times, and predictions is as follows, okay? So first, when we left the office, leaving office Friday at 6, the elapsed time was 0 minutes, and our initial prediction of how long we had left to go was 30 minutes. So our total predicted time was 30. Now, 5 minutes later, we reached the car after 5 minutes, okay? So the elapsed time is 5 minutes. Now, we saw that it was raining. And so from that point, we predicted our time remaining was 35 minutes. And since 5 minutes have passed, this means that our new predicted total time value was 40. Then, when we exit the highway, we thought that we made some good time, so maybe we cut 5 or 10 minutes off. So 15 minutes later, we exit the highway at time equal to 20, and now our predicted time to go is only 15 minutes. It's no longer that big prediction. So our predicted total time now is the current time that we've elapsed plus the 15 minutes, which is 35. Then we get onto a secondary road behind a truck after 10 minutes, and so we think, okay, now I'm going to be a little bit slower. So we predict 10 minutes to go, meaning my total predicted time is now 40 minutes. We enter our home street, and so after 40 minutes, we have 3 minutes left. We're at 43, and then we arrive at 43. So what this did was we had an initial prediction of how long it would take us to get home, but after every significant step where we observed new things, we updated our prediction. Okay, so here's the difference between Monte Carlo methods and temporal difference methods. If we had used Monte Carlo methods, what we would have done is on the left here. We would have driven the entire way home and said, okay, it took 35 minutes, or 43 minutes, sorry. So we would drive the entire way home and arrive here at time 43. Then what we would do, since we've generated the entire episode, is we go back to each of those states right here. All these dots are the states and all the actions. And we update all of those to bring it closer to 43 minutes. Because what we did was we generated an episode. We said it took 43 minutes, therefore all of my predictions should have been closer to 43 minutes. So this is, in Monte Carlo, we generate the entire episode, we get the return, which here was 43, then we go back to all the states and we update the values of those states to pull them closer to 43. However, in temporal difference learning, which is over here, what we do is, after each state, we make an observation. Okay, it's essentially the reward. And after each state, we pull the value of that state with our update function closer to our new predicted value. So initially, we thought it was going to be 40, then we thought it was going to be 35, then we thought it was going to be 40, and finally 43. So again, Monte Carlo, you generate the entire episode without doing any updates, and then you update everything so that your belief is closer to the return. But in temporal difference methods, what you do is after each action, you update the value of the states based on the new reward and the new observation. Okay? So that is Monte Carlo here on the left, temporal difference learning on the right. That's the big difference. So, temporal difference learning advantages. So dynamic programming requires a model. Monte Carlo and TD do not. Monte Carlo waits until an episode is finished to do an update, whereas TD is online and incremental. And sometimes episodes are just very, very long. And so when you do a really long episode in Monte Carlo, sometimes the updates can be really poor. Okay, they won't be very accurate. Versus temporal difference learning is going to update at each state action pair. And continuing tasks have no episodes, so how would you use Monte Carlo in a continuing task, right? You can't. But temporal difference learning can be used for continuing tasks. So TD methods tend to converge faster than fixed size alpha Monte Carlo methods, but that's not proven yet. Someone asked in the chat what it is in terms of time or cost complexity. We're not going to go into things like convergence rates and stuff in this course. I'm more about teaching the algorithms, but all of that is available in the textbook if you want to look at that. So here's a prediction example, okay? Let's say that you have 8 episodes. Oh crap, I forgot what this example was. Oh dear. You know what? I'm gonna skip that example because I can't remember how it goes. Oh, that's embarrassing. Yeah, I can't. Oh, geez, I can't remember how that example goes. So I'll just delete that. Whatever. It wasn't a good example if I can't remember it. And remember the car driving home example. Actually, it's in the book. It's in the book. Go read that one in the book. There you go. That's how I cover myself. That's up to the student to learn that one. Okay. So, temporal difference control. We just did temporal difference prediction. Prediction, remember, is the value of states and actions. Now we do control, and control is updating the policy. So, we've discussed already temporal difference for prediction. So that's given a policy, what is the value? But now how do we update the policy? Well, temporal difference learning also uses GPI, so it's really easy. So like Monte Carlo, we have the same exploitation versus exploration trade-off. And like Monte Carlo, we can have on-policy TD and off-policy TD. So what is on-policy TD control? In on-policy, we need to estimate Q pi of SA for the current behavior policy pi and for all state action pairs SA. So we can use the same TD method discussed before for estimating V pi of S, but now we're just using Q of SA. We know the difference between those now. And then what we could do is just update the policy pi to be greedy with respect to Q pi SA. So this is no different than anything we've discussed before. It's just like Monte Carlo control. Once we have values for all the actions at all the states, we're going to update our policy at a given state to just maximize the value by taking the highest valued action. Okay, so the first on-policy TD control algorithm, actually the only one that we'll be learning in this course, but a really famous one, is called Sarsa. So Sarsa is an on-policy TD control algorithm. Episodes consists of state, action, reward. Okay, so up here, again, we're at some state, S of t. We take action, A of t. We get reward, RT plus 1. Now we're at the next state. We take an action, we get a reward. Now we're at the next state. We take an action, we get a reward. This is the general situation that we're in. Previously, we learned for TD to transition between episodes, states, and updates V of S, okay? So what we did before is we learned that to find V of ST, we use this formula. Now, the value of state action pairs using Sarsa is this formula. And I know it looks a little bit complicated, but it's really not. It's just saying that the value of a state action pair is equal to the previous value of the state action pair plus alpha times the next reward plus gamma times the value of the next state action pair minus the previous value. Okay? So what we do is the following. Okay, and the reason, by the way, that it's called Sarsa is the following. Or do I have that in the slide? Okay, yeah. So that's the formula for Sarsa. If ST plus 1 is terminal, then Q of ST plus 1, AT plus 1 is 0. Okay? So, for example, right here, this is using the value of the next state and the next action chosen to update the value of our current estimate of Q S of A. And so the policy update is greedy with respect to Q of SA. And the formula makes use of the following data. So if you look at this formula, the variables within this formula are the current state, the current action, the reward, the next state, and the next action. So state, action, reward, state, action, that is Sarsa. State, action, reward, state, action. So it's really easy to remember the formula for that, for Sarsa. So here is how we do Sarsa using epsilon greedy, because remember, sometimes looking at code can make things easier. Let me drag myself back up here. All right, so Sarsa using epsilon greedy. So to initialize again, we're going to have Q of SA, that's the initial value for each state action pair, with the Q value for terminal states being 0. Then we're going to repeat forever for each episode, or if we have a continuing task, it doesn't have to be episodes. So S is initialize the starting state for the episode, and then we choose some action, S, using epsilon greedy on each action. Okay, so this colon here, if you're familiar with that syntax, it just means for each action. So what we do is we're going to use epsilon greedy, right? Because this is Sarsa using epsilon greedy. And that's the action that we're going to choose to do here. And then we repeat for each state of that episode. The reward and the next state are generated by taking action A at state S. So we take action A at state S, we get a next state, and we get a reward. Then A prime, we have to choose one more action, okay? So we choose A prime from S prime using epsilon greedy on the next state. So Sarsa is a little bit more complicated because in order to update our value, we need to have the value of the next action chosen by our policy as well. But the update is really, really easy to do in code. You just update the current value based on the previous value and all these variables that you already have. And then you set the current state equal to the next state and the current action equal to the last action. And so that's how you keep track of those variables. But we're not going to be implementing Sarsa in our assignment. We're going to be implementing Q-learning. Okay, so this is the real one, and it's so powerful, it's so great, and it's actually much easier than Sarsa. So it was invented in 1989. It was a really early breakthrough in reinforcement learning. It's an off-policy TD control algorithm. And there's one difference between Sarsa and Q-learning. In Q-learning, we have the exact same formula. However, what we do is instead of taking the next action and seeing what we get, we look at the next state and find the maximum value from the next state to update our function, okay? So again, Q of ST-AT, that's our current estimate of QSA. We update that by taking the previous value plus alpha times this thing, and that is the next reward times gamma times the value of the maximum action at the next state. The maximum action at the next state. That is the big deal of Q-learning. And then, of course, we subtract the previous value. So the learned Q value, this QST of AT, directly approximates Q star, which is the optimal value, the optimal action value function, no matter which behavior policy is being followed. So that means we could actually generate like random episodes and learn the optimal policy using Q-learning, which is incredible. So I'll show you the difference now, how easy it is to implement Q-learning using Epsilon greedy. So here's the initialization. Same thing as for Sarsa. We initialize S of A for each state in action. Then we repeat forever. We're going to have a starting state for this episode or for our continuing task. And then we're going to repeat the following. So we're going to choose an action to do at this state using Epsilon greedy, and we store that as A. We're going to take action A at state S, right? And we get the reward and we get the next state. QSA is going to be equal to the previous QSA plus alpha times R times gamma max A of Q, S prime, and A. And then S equals S prime, and that's it. So all we have to do, the only tricky thing here is that we have to loop over all the actions for the next state, find the action which maximizes it, and then plug the value here into that formula. And that's Q-learning. It's actually easier to do than Sarsa, believe it or not. So Q-learning is off policy. Why is Q-learning considered to be off policy? Well, if the policy algorithm estimates the value function of the policy generating the data, then the method is called on policy. Sarsa learns the value of a policy, of its own policy, which does some sort of exploration. Q-learning learns the value of a policy which does not explore, since it takes the next max action value. Okay? So, that's a big difference, and please read more on this chapter in the textbook to understand that. But, here's an example from the book, which is called The Cliff. Okay? So, in the cliff, you're trying to get from this start location to this goal location. Let me go quickly to the explanation of this, and then I'll come back to this. So in the cliff, the actions are up, down, left, and right. You're going to get a negative reward, -1, at each time step. So that means that in order to, if you're maximizing your return, what you're doing is you are minimizing the amount of time it takes you to get from the start to the goal. If you step onto the cliff, you get a reward of -100, and then you go back to the start. And so it's designed to show the difference between Q-learning and Sarsa methods' online performance. So what the hell does this mean? Okay, so the important part about Sarsa is that if you're using Sarsa with Epsilon greedy and you're using Q-learning with Epsilon greedy, let me see if I can draw this example. Let's say that we are right here on this tile and we're currently updating using Sarsa, okay? So what Sarsa says is, I'm going to update the value of this based on what I would choose at the next state. So this state has a bunch of different actions right here. So we can go up, down, left, or right. If we happen to go down, we're going to step on the cliff and we're going to get a huge negative reward. Okay? So what Sarsa does is it says, I'm going to update my value based on epsilon greedy selection at this state. So that means when it does its update and it selects the next action, it could choose to go down randomly with epsilon greedy. And then it's going to take that value into account when it does its own update. So it thinks that, okay, well, if I randomly chose going down here, it's going to say, oh, it's kind of dangerous to be here because the next state, the action that I chose at the next state led me to do something really, really bad. And so it's using the epsilon greedy policy and then updating that policy. Whereas Q-learning, what Q-learning does is it updates the value of this state based on the best possible action at this state. And so since it's the best possible action, you're never going to update it based on the action of going down. You're always going to update it based on the action of going to the right. Okay? So the point here is that Sarsa's updates of state action pair values include the randomness of epsilon greedy in it. But because Q-learning selects the value of the maximum action at the next state, it does not update its values based on the randomness. It does the randomness in its exploration, but the update of the value doesn't take randomness into account. So, Sarsa thinks that if you head right along the cliff, this is really dangerous, because every now and then, epsilon greedy is going to guide you off the cliff, and Sarsa does an update based on that. And that's really, really negative. And so what Sarsa is going to end up doing is taking this really safe path where you'd have to get really unlucky to generate a bunch of random moves in a row to not get to the cliff. But because Q-learning knows it's going to look at the maximum action, the value of the best action at the next state. It's not going to be taking these steps off of the cliff. And so it's going to be taking this optimal path, which is right next to the cliff. Because the updates of Q-learning do not factor in the randomness of the exploration. Okay? So, here's the two-line importance. Sarsa updates its value estimates incorporating the randomness of epsilon greedy. And so it does not like to go near dangerous things or near states that have negative rewards. Q-learning instead chooses the maximum action at the next state to update its values. And so if there is even a single really good action at the next state, it's not in danger of accidentally stepping off the cliff. It knows that that won't happen, and so it will generate the optimal path. Okay? So again, Sarsa will take this path, which is avoiding the cliff. Q-learning will take the path, which is close to the cliff and is therefore optimal. Okay. But here's the thing. This is something that's really interesting, is that in the cliff episode, if you actually run Sarsa and you run Q-learning, the sum of the rewards that you get from Sarsa is actually better than Q-learning. Well, if we just said that Q-learning is going to be producing the best path, why is Sarsa giving us better rewards? Well, it's giving us better rewards during training because during training, we're still using epsilon. So during the online training phase, Sarsa is taking the safe path. Okay? And by taking the safe path, we're avoiding the epsilon greedy heading us off of the cliff. Q-learning is going to learn the tighter, more optimal path, but during training, it could lead us off of the cliff. Okay? So, while Q-learning is still doing epsilon greedy and still learning, it's actually probably going to do worse than Sarsa. But what happens is, if we then take the learned policy and stop learning and then just apply the policy, the offline performance of Q-learning will be better than Sarsa. Why? Is because now we'll just be taking the best path along the cliff without doing any exploration. Whereas Sarsa's policy learned to avoid the cliff even though in the future there may not be any randomness. So I hope that's a little bit clear, and that distinction between Sarsa and Q-learning and on policy and off policy is really important. So Q-learning learns values of the optimal policy, and that optimal policy travels along the edge of the cliff. This results in it sometimes falling off the cliff during training because of the epsilon greedy action selection. Sarsa takes the epsilon greedy action selection into account and then learns the longer but safer path along the top. So on policy is going to learn values of the policy that guides it. Even though Q-learning learns the values of the optimal policy, its online performance, which means its performance during training, is worse. So Q-learning is going to learn the optimal policy, but during training, it's going to do worse. So don't always trust the training graph values, okay? In order to actually evaluate things, you need to take your policy and run it for a given number of time steps without the exploration. Okay, here's some possible exam questions. What does it mean to be an on-policy or an off-policy RL method? Why is Sarsa on policy and Q-learning is off policy? Why do Sarsa and Q-learning produce different paths through the example in the cliff? TD methods borrow ideas from MC and DP. Why do they do that? Sarsa and Q-learning algorithms. All of these exam questions, however, were for the closed book exams of yesteryear. You will have different questions than these because I'm not going to give you a question that you can just look up in the notes. Okay. So that's it for the slides, and that's it for the Q-learning. So let's discard this. And now what we're going to do is we're going to go through the assignment. And so I'm going to take a little bit more time this lecture, but it should only take me, I'd say, about half an hour. Hopefully, half an hour to do this. All right. Here is assignment 5. In assignment 5, we are using Q-learning, and we are going to do reinforcement learning for pathfinding. And here is the environment in which we are going to do that. I have done this up for you, and it should be pretty fun. I think this one is pretty fun. So here we have a pathfinding environment. It's a grid in which you can take the actions up, down, left, and right. Here in red, we have the agent. So the agent is actually going to be at a specific point on the map, and it's going to be guided by a policy. It's going to be moving around. It's going to be learning which actions are good and which actions are bad. So what do we see here then? So the white squares here are squares that we can travel on. So we can travel through the white squares. The gray squares, those are walls. So we cannot walk into those, and we can't walk off the edge of the map either. The green squares are the goals, and we want to get to the goals, okay? So these are the goal states. So what's going to happen is that if I do an iteration here, so the first iteration is going to put the agent into a random spot on the map. So where it has placed me right now, it's up here. So the agent is going to take an action based on the current policy. And the current policy is actually drawn here for you on the map. So what you can see is this little cross going up, down, left, and right. And what that indicates is the current direction that the policy thinks that you should move in order to get... Oh, and the whole point of this is to get to the goals as fast as possible. So let me actually just run this for a second. So I'm gonna crank this up to like 100. I'll talk about that in a sec. And then I'll crank this up to 100. We'll toggle the iteration. And let me put this up. Boop, boop, boop. And what we get in the end is the following. After we're done learning, what we get is the following. So once we've learned the optimal policy, we should get something like this. And it displays the following with the following, the policy with the following syntax. It displays all the directions that it thinks that you should head in with equal probability. So for example, if you're just to the right of the goal here, actually let me go down here. So the agent is right next to the goal, right? So it thinks it's saying I should head up in order to get to a goal. If I'm right here, for example, it's say going to the right. And that's pointing along the optimal policy, okay? Or the optimal path to the goal. If you see here, this one actually has up and left. And that's because whether we go up or left from this point, we're going to get to the goal as quickly as possible. Some places actually have 3, and so this means that I'm actually, if I go left, if I go down, or I go right, I get to the goal as soon as possible. And one of these spots actually has 4 spots, so we can go up, down, left, or right, and we will be equally as close to any goal. Okay, so how does this all work? Well, at the beginning, what's happening is that we're going to do a single iteration of this. If I can pull this up. Okay, so this is implementing the Q-learning algorithm. And what we have is that whenever we take an action, one other thing, if you are next to a wall, you can take the action of heading into the wall. However, the result of that action is that you will just stay in the same place and you'll get the negative reward. So you can take up, down, left, or right is legal from any state in the environment. However, if you try to go off the map or you try to go into a wall, all that happens is you stay in the same place. So when you implement that part of the assignment, remember that. Okay, so let's just have a look at the first traversal here. So if I click right here, you can see mouse mode is print values. So in order to help you with debugging, if I click on a cell, then up here in the console, it says, well, I clicked on cell 7, 3, so that's 0, 1, 2, 3, 4, 5, 6, 7 in the X direction, and 0, 1, 2, 3 in the Y direction. So the values at 7, 3, here you see there are 4 different values, okay? So all of my value estimates are going to start at 0. So each state is going to have 4 actions, up, down, left, and right, and we're going to be maintaining and updating the values of taking each of the actions up, down, left, and right at each of those locations. So over here, what you see is, under values, are the values of actions up, down, left, and right. And they're currently all 0. And the policy, you see the probability that I should be taking each action. Okay? So the probability right now, at the start, I want to randomly choose any of the 4 actions. That's it. So by randomly choosing any of them, well, each of them is set to 0.25. So let's do a single iteration now using the solution code, and we'll see how this updates. So when I click single iteration, it will choose one of the actions from here, from the policy, and right now they're all set to be done with equal probability. It's going to get a reward, and the reward, if I can just show you, is defined in the maps file. Okay? So how I define these maps is as follows. So the default map, if I have a terminal or goal position, that's marked by T. Okay? If I have a wall, that's marked by an X. Otherwise, I have a value, and that is the reward that you will get from taking any action at that state. So, all of the open tiles have a reward of -1. Why do they have a reward of -1? It's because if I have negative rewards for movement and positive rewards for the goal, okay? So let's say, for example, I put my goal reward up to 100. Then what's going to happen is I'm going to eventually learn to go towards the goal as quickly as possible because I'm trying to I'm trying to maximize rewards. And since rewards are negative, you're taking the fewest actions possible. Okay, so let's click single iteration and see what happens. So it chose to randomly go up, okay? So it chose to randomly go up, it got a reward of -1, and now it's here. But let's go back and click on this state again. So we're going to click on it, and what we get is the following. So here are my values now. So up is the first action. So I took the action up, and I learned that my new estimate of this action is equal to negative 0.1. Now, why is it negative 0.1? Well, that's because my alpha is equal to 0.1. And my reward was negative 1, so negative 1 times 0.1 plus the previous estimate of 0 is negative 0.1. So what happens then is after I've updated the values, now I have to update the policy. And so the policy states for every action, I want to generate, for every maximum action, I want to take that action with equal probability. So if I have a negative 0.1 and 3 zeros, the 0, that's going to be the maximum value. So what I should do is take these actions with equal probability. So what I have down here now is my new policy for state 7.3 says take action 1, 2, or 3 with 1/3 probability each. Okay? And if you see over here, what you've done is you've eliminated the up. There you go. Let me actually load the tiny environment, and I'll do a couple of moves until I get right next to the goal. Okay. So here I am right next to the goal. Hopefully, what you're going to see is that the next action is going to take me to the goal. Please take me to the goal. Crap, it didn't. Okay. What it did do was it tried to go down, and by going down, it hit the wall, got a reward of -1, and now it doesn't like going down anymore. So that's what you see right here. Let's try it again. Okay, good. It went toward the goal. Perfect. Now I can explain this. So you see, now it's pointing to the right. Well, why is it pointing to the right? Let me print that out again. So I'll click this value. And so what it did was, we have the values. Let me move my... what am I doing? Let me move my camera. So over here, we can see these values. So I have new values now. This is up, down, left, and right. So we haven't tried up yet, so we don't know anything about it. We tried going down, and we got a reward of -1. And so what we did was we multiply alpha by -1 to get negative 0.1. We haven't tried going left yet, but we did try going right. And when we went to the right, what we did was we got a reward of 100, right? Because this is the reward of getting to the goal. So we got a reward of 100. Our alpha value is 0.1. And so now the value of going right has been updated to 10. So we look through here, and to update our policy, what we're going to do is say, for each of the maximum valued actions, take each of those actions with equal probability. So action 0 has a value of 0. That's up has value 0. Down has value -0.1. Left has value 0. Right has value 10. Therefore, I look for the maximum value. Action 3 has the maximum value, and there's only one of them. And so I update my policy to make sure that I go to the right with 100% probability. And that's how this gets updated. Great. Okay. So that's what you're doing for this assignment. You're implementing a few functions. You're implementing the Q-learning value update rule. You're implementing the Q-learning policy update rule. And you're implementing how the agent moves around the map. That's it. Okay. And if I click toggle iteration here, it will learn, and it will do these at like 60 frames, 60 actions per second. And if I want to make this even faster, I can just say, okay, do 100 iterations per frame. Okay. Now, if I look up here, let me do one more example of this. So let's say now I'm right here at this state where my mouse is. It says to go down all the time. But we know we can go down or we can go to the right, and they'll both give us the same value. But let's just click. So if we click here, we're going to look at the values. And so up, down, left, and right. So we said that down and right should be approximately the same value. And so down and right are around like 88 and 83. And so it takes it a long time to actually converge to the point where they have the exact same values. So let's do like thousands of iterations to the point where now when we click it, we have a value of 88.999 and 88.999. And only at the point where they're very, very similar will you actually have it going to the right or going down. So if you run your simulation and you're not getting like, go right or go down for this example, it's probably just because you haven't run it long enough yet in order for it to learn that the values are almost identical. Okay. And then if we go down here, we see, okay, going up has a value of 70, going left has a value of 70, but going down and right have values of 88. Therefore, I want to go right or down with the same probability. So that's how this assignment works. And all you have to do is fill in a little bit of code. So let's go over exactly what you have to do now. So here's my solution. I won't go over that. First of all, there is a class called environment. Okay. So in the environment class, you have a few variables here. So first is the grid. That's the actual array that stores the values. The grid has a width and a height, and it has the actions which are legal as well. Okay, so the actions are move up, down, left, and right. And it also has a goal reward. So a goal reward is gotten when you are at a state and you take an action which leads you to a goal. So for example, if I am at this state and I choose left, it will give me a reward of 100 because I've put 100 in here. If I choose up, down, or right, then it will give me a reward of -1. Okay? Now, I've put this in here because you can actually still learn with a goal reward of 0 because the Q-learning algorithm is going to, it's a continuing task and it's going to learn to minimize those rewards. So, I have one other thing to say that I forgot to mention, the other rule about the environment. Let's toggle the learning here. Okay. The other rule is when you reach the goal location, on the next time step, you teleport to a random location on the map. So here I'm at the goal, teleport to a random location. Here I'm at the goal, teleport. Here I'm at the goal, teleport. I can also do the following. Let's go to the large environment for a second. Let's give the goal reward something interesting. And now let me turn on the learning. Okay. Okay, so we've toggled on the learning. We've got a bunch of stuff. That's good. What I can actually do here is I could insert some walls if I want to. So you can edit the map here, right? I can also clear a tile. So I could clear it there if I want to. Uh-oh, I made a mistake. I'll fix that before I release the assignment. I could also insert a goal node if I want to, and then do learning again. And the cool thing is, I learn to go to the new goal. See how all the things here have pointed toward the new goal? And if I insert a wall down here, then I toggle the iterations, then it will learn that these guys should go down instead of going up. So you can edit the level too, or as well as print the values, okay? So tiny environment, if I say, let's insert a wall right here, and we'll insert a terminal node down here or up here, and then we toggle the iterations, that the policy that it learns will be the one that gets us to any goal the fastest, right? So here it will go right, here it will go right, etc. So that's the other rule, is that when you get to a goal, you teleport the agent to another random location. So this is technically a continuing task. There are no episodes here, because what happens is there's no episode saying go from here to the goal. What we do is, and we just keep teleporting to random places in the map. Okay, so let's go over the code. Those are the variables for the environment. I've got getting functions for you and setting functions, so you can get the XY location and you can set the XY location. You're probably not going to be calling set, but you will be calling get. Get actions, that will return the legal actions. We have an is out of bounds function. So is out of bound function will tell you whether or not a given location is actually out of the bounds of the map. We have is blocked. So is blocked will return true if there's a wall at that particular location. We also have is terminal. I should say is goal. I'll probably change that to is goal before I release the assignment. So here is goal it's going to be true whether or not this is one of the green locations on the map. Okay. I also have get reward, and the reward get reward calculates the reward that you do from an action. And essentially what happens is if you're taking any action, you get one of two rewards. So if you're heading toward the goal location, so if your action takes you directly from the current state to a goal, you get whatever is in this box right here as your reward. Otherwise, if it takes you to another state, you get a reward of -1. And that's what that function does, and it's already calculated for you. Okay? So everything in environment is done for you. Those are the helper functions that let you get at the variables of the environment. Next, we have the user interface, which you don't need to worry about. And then you have RL student. So RL student will be what you are filling out. Okay? So we have, the first thing we have in here is the config, just like you've had configs and other things. So this .config, those are the learning configuration settings. And inside that, we're going to have alpha, epsilon, and gamma. Okay, so alpha, epsilon, and gamma will be inside that variable. We also have a pointer to the environment. So this .env, you could call this .env.getXy to get the values of the cells. We also have Q. So this is going to be our values array. And so QXYA is the value of doing action A at state XY. And your policy PXYA, that's the probability of doing action A at XY. So these are three-dimensional arrays indicating, and our states here, remember in our notes, we have QSA and we have PSA, but our states here are two variables. It's an X and a Y variable. So instead of QSA, like this, we've split the state up into its X and Y values. So it's QXA and PXA. Q is the values, P is the policy. This .state, that is the current location of the agent on the map. So currently, this .state would be the X equal to 0 and the Y equal to 3. Okay, so that's this .state. I have done this all for you. So the initialization of the Q values and the policy to equiprobable random are already done for you so that you don't ever have to mess around with constructing three-dimensional arrays. It's easy, but some people are having problem with JavaScript in the course. So that's done for you. Init is called at the start, and it sets up all zeros as your initial values, and it sets up an equiprobable random policy. So if I reset back here and I click here, you can see that the policy is equiprobable. Oh, you can't see that. Let me click it a few times. You can see that the values are all zeros, and the policy is equiprobable random. Okay? Now, here's where your stuff starts working. So the first thing is learning iteration. So my GUI, every frame, 60 times per second, calls this function. It calls the learning iteration function. And inside here is where you write the Q-learning algorithm. I have written the pseudocode for you. Okay, so what do you have to do here? There are 7 steps. The first thing you have to do is if this .state is terminal, set it to a random legal state. What does that mean? Well, it means that right here, if we ever find that we've gotten to a terminal location, we have to teleport ourselves to a random spot on the map. Okay? So you'll have a little while loop there that says while this .state is not terminal, set it to another random spot on the map. Okay. That's the first thing. The second thing is select an action A to perform from our current policy. And that is going to be done in the this.selectActionFromPolicy function, and I will show you how to do that in a bit. The third thing you have to do is get the reward from doing action A at the state from the environment. So what that does is you just call this .env.getReward x, y, a. Now, very importantly, in this assignment, actions are being represented by an integer, okay? And that's the integer into the action index. So for example, please, okay, I'm waving my hand so you know where to go, so I can tell you, go to the part where I'm waving my hands. Action here is an integer. It's an integer. That integer is the index into the this.actions array. Okay? So you know what? I'm going to make this action index. There you go. So now when you get the reward, you're not passing in the XY action, you're passing in the action index. Got it? Okay. So get the reward from doing action A at this.state from the environment. So when you select action A here, this action A, you should store that based on its index of all the different actions. Perfect. Calculate the next state by doing action A at state S, and that's going to be the this.getNextState function. Then you update the current Q value based on the Q learning update rule, that is this.update value. Then you update the policy based on the state, okay? So you update the current state's policy, and that's this.update policy, and then you set this.state equal to the next state that you calculated in step 4. So this function, a bunch of this is literally just calling functions in the correct order. And the functions are going to be the things that do the logic, okay? So let's look at those functions that you have to do. So the first function is select action from policy. So this function should select an action to perform at a given state given the current policy and epsilon greedy this.config.epsilon value. So choose the action based on epsilon greedy and the probability stored in the policy. Pxya is the probability of choosing action A at state xy. So for example, if your P xy is equal to something like values of 0.5, 0, 0, 0.5, then what you have to do is you go through, you're going to see which of the values has the maximum value. So that would be action 0 and action 1. So let's just say we have let max actions equal 0 and 3. Okay, so we have our PXYs. We're going to have a new array, which is, into it we put all the actions which maximize the value. And then in order to select the action, we're going to return the action or a random action from this array, right? Because this stores all the actions that did the best thing, and here we're going to return that. And this actually should be max action. So I'll fix that. That's the integer that you're going to be returning. I actually have to fix that. This is going to return action, which is integer index of action to perform based on the policy. Okay. The next function is the getNextState function. So this function should return the XY state obtained by doing the given action at the given state. So note, moving off the map or into a blocked tile results in staying at the same state. So the arguments to this are the state. This is actually going to be, the state is, oh no, sorry, that's correct. Ah, Jesus. The getNextState, the action is the integer action index to do at the given state. So we're going to be passing around actions by integers, remember? So up is 0, down is 1, left is 2, right is 3. And that's going to return the next state. So for example, if we're here in the tiny environment and we are at state, let's say 0, 0, and we try and do action 2 or whatever, which is moving to the left, we're going to stay in the same spot, okay? If we're here and we try to move right, then we're going to the right, so our next state is going to be here. Very simple function to write. The next function is the update value function, where you are going to implement the QLearning update function. So this function should update the Q value of a given state, action pair, based on a given reward and a next state. So in here, you're going to read the values of this.config.alpha and this.config.gamma in order to compute things. So you're going to have the state, the action. This is the integer index of action. This is the reward that you obtained and the next state that you obtained. Okay? So you're going to implement the QLearning function based on these things here. And that's literally just going to the slides and taking state, action, reward, and next state and plugging that into the QLearning function. I think before I release the assignment tomorrow, I'm going to put in a couple of hints in here for you on how to do that. And then what you do is the last function that you have to implement is update policy. And this function should update the policy at a given state to equiprobably choose from all actions that maximize the Q value at that state. And so the argument input is a state, an XY state, and it's going to update the policy, and this is the pseudocode for that. So max action value, in order to do that, let's do a quick example in code. So let's say we have a QSA, right? So we're going to have QXY, and we have 4 actions. And let's say that our 4 actions are going to have values 0.2, or let's say 1, 3, 3, 3. Or let's do this, 3, 1, 3, 3. Okay. So what we want to do then is we're going to find the following. We're going to say let max action value equal, and then we're going to go through this array and we're going to get the maximum action value from that array. So the maximum action value there, is 3. Then we're going to have let max actions equal a new array. And then what we're going to do there is we're going to iterate through the indices of here, find all of the indices which match the maximum value, and put them into here. So this is 0, 2, and 3, because actions 0, 2, and 3 gave us the optimal values. And then what we do is we update our policy, PXY, to be equal to, well, if it's in the maximum actions, then it's 1 divided by max actions.length, and if it's not, then it's 0. Well, what does that mean? Well, let's say we have PXY, and that's going to be, well, this is going to have 4 different values, right? And we're going to update them in the following way. So currently I'm at action 0. So if action 0 is present in the max actions array, then this is going to be 1 divided by 3, because it's 1 divided by the length of the max actions array. Now we go to index number 1. Is index number 1 in this array? No, it isn't. So it's 0. Is index 2 here? Yes. So it's 1 over 3. And is index 3 here? Yes. So it's 1 over 3. So what we're doing is we're saying, okay, which actions maximized this value? And so if we have 3 of them that maximize the value, then we're going to set the probability of choosing each of those actions as 1/3. And that's how we do the update rule, okay? Alrighty. And that's it. That's the assignment. It's actually not that bad. I think this might take the least amount of time of all the assignments if you don't run into some weird indexing errors, okay? Just remember, the only tricky thing here is that in here you have, for select action from policy, you're also implementing epsilon greedy. Okay? But I'll put in a couple of other notes there so that you have that for when you go to do the assignment. And that's it. That's assignment 5. You are implementing from the ground up, from scratch. Well, okay, technically I've given you the arrays, but you will be able to say that you implemented Q-learning from tabular Q-learning from the ground up, from scratch, and you were able to use it to learn the optimal policy for pathfinding. Okay? And that's a really cool thing to be able to say on a job application. Whew. Okie dokie. One last thing before we do this is just an interesting fact about the goal reward. So the goal reward is important. Why is the goal reward important? Well, let's say that the goal reward value was 0. Okay? So if the goal reward value is 0, and I turn this up to a bunch of iterations, and I say toggle iterations, then let's look at what happens down here in our graph. Okay. So in our graph down here, we get to... Oh, I really need to restart this. Hang on. Tiny environment. Let's go to 100, and we'll have a goal reward of 0, and we'll see how the graph goes down over time. Okay. So at around... Let's say at 8,000 iterations, we finally get under a value of 6. Okay? So we've gotten to a value of 6 within 8,000 iterations. Let's try that again with a goal reward of 100. Now let's see. Toggle iterations. Oh my God, look at this. In less than 2,000 iterations, we got under a value of 6. And so actually, let me do that again, but I'm gonna do it with a far slower... Oh, geez, I'm at the wrong thing. Tiny environment, goal value of 100, toggle iteration. Okay, so we're gonna look at this. We're gonna see how long it takes us to get there. To get to an average value of 6. It's going down and down. So what this graph down here does is it averages the total number of iterations that it took to get you to the goal from any place on the map. And so if your learning is happening properly, this should be going down. Okay, so we can see here that after 1,400 iterations, we got to a value under 6, which is a good value. But again, I'll go back to tiny environment and I'll keep this at a 0 reward. If I put this up, then it's going to take us much longer to learn to get to a value of 6. Okay. So still, after like 6,000 iterations, we're still far away. So what this is doing is with a goal reward of 0, sort of the only feedback that we have is that when I go from this state to a goal, nothing bad happens, right? So I get a reward of -1 everywhere, except when I head to the goal, I just get a 0, right? So there's no huge update in the value because everything else gave me -1, this gave me 0, therefore my value isn't really updated that much. The higher I put the reward on the goal, the more my value gets updated when I move toward the goal. So the more immediately I think, hey, this is a really good action. Okay? So what I did here is I just wanted to show you that because it is important. When you're talking about reinforcement learning, how you formulate the rewards is very important. Okay? So the -1 part will help you shape the path because by maximizing the returns, you're minimizing the number of time steps. So that helps you get the shortest path. But going toward the goal is giving a high goal reward is going to help you more quickly learn the value of the goal. So when you go to test your program, you should still be able to learn, like if you pump this up to like 10,000, eventually you should still get this graph. It should still solve it, right? But let me just do, so let's put 100 in here and we'll toggle this, right? So let's say when we get down to, I don't know, 10. So when do we cross 10 here? We cross 10 at 30,000 iterations. 30,000 iterations. Let's put the goal up to 100, put this at 100, and now we'll toggle it again. And we're already at 10 after 7,000 iterations, right? So the value that we assign to our goal is hugely beneficial, okay? All right, that's it for the assignment. That will be released sometime midday tomorrow. Take tonight to finish up assignment 4. And with that, I will see you tomorrow.